I recently co-authored an annual review about Gaussian processes for time domain astronomy. And I'm going to draw on some of that material here. And it's kind of exciting because there didn't used to be sort of a good, I don't know if it's good, but there didn't used to be an astronomy specific reference that I could give for Gaussian processes. And this review is like the brain dump of all of the things that we know about Gaussian processes, hopefully in a language that's accessible for astronomers. And so it's worth checking out. It's on arXiv and me, and it's the only paper that we've ever written together. So that's enough information to find it. And it also lives on GitHub because naturally we wrote it with Rodrigo's Show Your Work package. So there's code examples and all of those kinds of things with a live version of this on GitHub under my username. And it's something like GPs. So you can get the most up-to-date version there. We're actually still working on revisions. We've had some feedback from the community, but if you're an expert in Gaussian processes, or if you're not an expert in Gaussian processes and happen to read this and have any suggestions, there are lots of typos and stuff like that that we've heard about, but other things, please let me know. We have until November 15th to continue making changes. So the sooner the better. Good. Okay, so Gaussian processes. That's what we're talking about today. So a part of the idea with this review that we wrote was trying to like demystify Gaussian processes a little bit. Like they're pretty widely used. People talk about them all the time, but sometimes it feels a little magic. And I'm hoping that also today helps a little bit with that. If something isn't clear, if something feels too magic, please interrupt me. I've prepared far too much material. And so it's better that we have a conversation as we go. I don't have to get to everything. Because I can talk forever about this. Okay, good. So I wanted to start with a little bit of discussion about why you might use Gaussian processes in some use cases. The main one that I'm going to talk about today, which is, and sort of the motivation that I'm going to come from is as a model for correlated noise in data. That's what I've mostly used it for. And there are lots of places where that appears, and I'm going to talk about that a lot, so I'm not going to dwell on it now. But there are a few other places where it gets commonly used. So for example, if you have a stochastic physical process that you want to model, a Gaussian process is often a good model for that. So for example, if you are used to thinking about the power spectrum of your data, a Gaussian process is a way of modeling your data directly under a power spectrum model. That's one example. So for example, in astroseismology or quasar variability, these kinds of things, those are time series applications where you have a physical process specified by its power spectrum. And GPs are commonly used in that context. And then another place is if you're doing interpolation or extrapolation or smoothing of a data set where you sort of want to be somewhat agnostic to exactly what's going on. So for example, in astronomy, it's becoming more common to use Gaussian processes as emulators for very expensive models, for example. And there you're interpolating in some high dimensional, unevenly sampled space. And I'll talk about a little bit about how we would do that later on. Does anyone have any other examples of Gaussian, like broad Gaussian process use cases that it's not a test? Those were sort of like the big categories that I could think of, and we'll sort of talk about some more concrete examples as we go. But I wanted to start with a sort of motivating example, just to make things a little bit more concrete, and I'm going to introduce the math behind Gaussian processes, which is why we're on the board. Okay, so one of the things that I've spent a huge amount of my life doing is taking photometric time series and fitting exoplanet transit models to those data. So that's terrible, but whatever. There's some measured time series that has error bars, and I want to fit a model to it. That model looks something like this. It has, an orbital period. It has some, radius of the planet, some impact parameter, eccentricity, some set of physical parameters that describe this model. And in particular, we might write that model as some function of time, let's say, that's parameterized by some parameters. So in this particular case, those parameters, theta, would be the physical parameters that I just described, like the orbital period. Okay, good. So I have some points with error bars. I want to fit this function to those points. What do I do? So there are a few different ways that you might go about this. And one very non-astronomy and statsy way of writing this would be that my data, yn, is drawn from a Gaussian where the mean is my f here that I wrote down right here, evaluated at some time tn. And I have some error bars, sigma n. That's visible on Zoom? Okay, good. So this is one way that you might go about trying to fit this. So this gives us a sampling distribution for the data, and this corresponds to a likelihood function that I'm going to write down in just a second. And then we can do things with that likelihood function, like maximizing it or something like that with respect to the parameters theta. So what does this likelihood function correspond to? Well, I can look up what the equation is for a Gaussian on Wikipedia, and what I find is that the probability for my yn given theta is equal to 1 over the square root of 2 pi. I have this part of Wikipedia ingrained in my brain. 1/2 I know. It's worth it though, I promise. Did squared over n squared. That's the equation for a Gaussian. All right, but I have more than one data point. I have lots of data points. And so what I do is I write down a product in front of that. That's combining all of the data points. When we work with probabilities, we normally don't work in linear probabilities. We prefer to work in the log. So I'm going to take the log of this whole equation. Still worth it, I promise. That gets rid of my x here. I get a sum out front here. And I get one more term here. Good. So this is my log likelihood function. And so, like I said before, this is a function of theta, my parameters like orbital period, planet radius, that I can maximize to find the best fit parameters. Or I can combine this with a prior, run MCMC, and get some posterior distribution over the, there's sort of all sorts of things that we can do that I'm not going to go into the details of, but this is sort of the fundamental quantity in any data analysis. Now, I wanted to quickly mention here that so this thing right here might look familiar. So in astronomy, this is something that we would call chi-squared. right? It's the normalized residuals. And so I like to emphasize this here because this is a way of deriving chi-squared minimization. That's equivalent to assuming that your error bars are Gaussian and maximizing the likelihood. Those two things are equivalent. This term right here for fixed error bars is a constant. So it doesn't matter what the value is in order to maximize. But for reasons that you'll see in a second, it's extremely important that I keep that here for now. Actually, you're going to see that right now. Any questions about that? Yeah, perfect. Can you use the mic on the table? The ceiling mics aren't on.
Sure. Oh, I don't know. It wasn't a question that needed amplifying. You know, I kind of wanted to whisper it, but
okay, whisper it into the mic.
You said, you know, when you wrote this first with the, you know, with the capital N, and then you erased, right? Yeah. You said, okay, I could write this. Right. And I mean, did we make any assumption when we wrote this? I don't know if this is something you're going to go into. Is this always valid? Yeah.
Good. Yeah, we're going to talk about the assumptions a little bit. Sort of the big one is that that the distribution was Gaussian, that our sampling distribution, so that the error bars are Gaussian, which we're not going to go into too much detail for whether or not that's a good idea. We will come back to not. We won't come back to not. We're non-Gaussianity is written in my notes. But there's some other assumptions that we're going to come back to in just a moment. Good. But an aside I wanted to make right now when I write this, which is sort of it's like only tangentially related to Gaussian processes, but you know, if there's one thing that you come away from this discussion about is something. So there's like a class of models that, for whatever reason, in astronomer lingo, we've called jitter models or something like that. And that's basically, let's say your model is misspecified somehow, or your error bars are wrong, maybe underestimated, and you want to somehow correct for that fact or take into account the fact that your error bars are wrong or your model is misspecified. One common way of doing that is to replace your sigma n's by some sigma n squared plus s squared, where s is now a parameter of your model. And if I do that, that goes in here. We get an s squared here, and we get an s squared over here. Otherwise, everything stays the same. And this, people do this a lot in astronomy. This is actually something that you should pretty much just always do. And the reason why is because we still have our quality of fit term here. So this is like trying to get the parameters theta, but also s to be to like, you know, best describe the data. But if you just have this term, you would make s bigger and bigger, and that would maximize your likelihood. So so this would blow up to infinity if you only had this first term. But because of this second term, so this is the goodness of fit, and this is like the specificity or something like that. So this is a term that is trading off with this one, trying to make s as small as it can be while still describing the data. So there's this like beautiful tension that happens when you write this equation like this. That means that it's sort of, it's similar to like blowing up the error bars such that your reduced chi-squared goes to 1. It's not totally the same thing, but it's sort of in that direction. So so basically everyone should just always do this. You add one parameter to your model, it doesn't hurt anything. It's just like always a good idea. I think you were great. So the question was, is this SN or S? And there are sort of lots of different things you could do. So here it's just S. It's not SN. You're fitting for one shared parameter. You're saying that all of your error bars are underestimated by some amount, or you have an effective model where your model is entirely misspecified across the whole domain by some amount. It's not a great, it's a pretty rigid model, but it, in fact, it's, you know, it's often good enough. you could maybe come up with something where there, this could be a function of something, or there's some other things you could come up with. But here, I'm just adding a single parameter. Any other questions? No, same question. Okay, great. Good. So that was a bit of a oh yeah.
What if you're like simulating different sigma n values and you want it to be fixed? Would you still put in a jitter term, or would you ever like imagine keeping it at like a fixed sigma n? So you're simulating observations and you want to like iterate over different sigma n's, and adding in an s would allow that sigma n to be different, or yeah, to not be what you're simulating.
Yeah, so I think so this, I'm not sure I'll totally answer your question. This describes a new way of generating data where so under the usual model, without the S, when you simulate data, you have to choose some settings for sigma n, and adding this in, you would generate your data with extra noise in it, but the error bars that you reported to the person you're simulating to would be smaller than they should be by this amount. So that is a reasonable thing that you could do to like see how someone's analysis depends on the error bars being underestimated, for example. Any other questions? Yeah.
That the last term is the kind of trade-off.
Yeah.
But I think there's just normalization term. So it's not intrinsically, it's about trade-off, which is
Okay, great. So the question was, isn't the second term just a normalization? Why am I saying that there's a trade-off? And so interestingly, it is a normalization term, but another sort of an equivalent normalization term is the Bayesian evidence integral. And that gives you some information about the quality, like how believable your model is under the space of the distribution over models. And so the same thing is happening here. So it is a normalization factor, but it introduces this like exactly the right trade-off that we want. Those are identical things. We can talk more about that later. This will come up a few more times as we continue to go. Great. Good. Okay, so that's page 1. So many. No, it's great. Good. No, I wanted everyone to think about jitter because it's relevant. You'll see. Okay, but the thing I really wanted to get to, right, is that anyone who's ever looked at data that we work with for modeling transiting planets, it doesn't look anything like this. In fact, it's like some like wonky thing that looks like this, and there are tiny little transits on top of that, right, that we're trying to model, right? And so that's the real situation. And the problem here is that it's sort of hard to write down an F that describes this thing, right? So it's hard to like, what is this? So there are there's the stars doing funky things. Your instrument is doing funky things. There are all sorts of things going on here. And it's hard to write down some like first principles deterministic model that generates this thing. And so that's the problem. So the like standard way that people deal with this is they would try to do some filtering or something like that to remove this variability before fitting their transit. That has problems because you often over subtract or something like that. Another common thing would be to sort of ignore most of the data and only fit for some polynomial trend or something like that to like correct just around the transit. That's actually not such a bad idea, but we'll talk some more about that in a second. Question, yeah.
What filters do people use to do that? Is it like a Fourier, like a high pass filter usually?
So the question was, what kinds of filters do people use? And there's like a huge literature about that. And some people even use Gaussian processes, wavelet filters. There are lots of different things you can do. The problem is that a lot of the time the variability timescales are very similar to the transit timescale that we're interested in, and so you can run into some issues depending on exactly how you construct your filter. So there's actually a lot of thought that goes in, there's a lot of thought that goes into designing filters that are suitable for specific targets and stuff like that. But I like to use Gaussian processes for this. That's why I'm drawing this. And sort of the like motivation here is that while it's hard to write down a deterministic model, oftentimes in real data, there's some sort of like characteristic properties of this process. So there's some like characteristic amplitude of the variability and some, correlation length, some time scale of the process. And this is starting to look like something where, I might write down the power spectrum or the autocorrelation function of this variability. And I said at the beginning that that's a place where you might want to use a Gaussian process because it gives you a way of evaluating the likelihood function of your data in the data space under this stochastic process for the background. So how do we do that? I'm going to rewrite this equation yet again. And I think I might even try to write it up here. So, okay, so I'm going to define some quantities. So I have some vector r that are the residuals. So it's going to be y1 minus f evaluated at t1 up to yn minus f. No one can see that anyways. And then I have some covariance matrix C that's a diagonal matrix with the sigmas along the diagonal. And I have zeros off diagonal there. Great, so that's exactly the point. So here, there are a few different places where we've assumed that the errors are uncorrelated, as Rachel said. One is when we did this sum right here, we were asserting that there's no, like this data point doesn't care about this data point at all, right? They're totally uncorrelated. The noise process is unconnected between them. Similarly here, when we have a covariance matrix with all zeros off diagonal, that's saying the same thing. It's saying the noise process is independent for each data point, doesn't care about each other. So with these definitions, I can rewrite my likelihood function y given theta as a matrix equation. And if this doesn't feel super familiar, that's okay. Good, where yes, it's visible on Zoom. I don't know if it's visible in the room. So I have my C inverse here, and then this is the determinant of 2 pi C. So just for some notation points. So if you squint at these things, look on Wikipedia, this is equivalent to this without the S. And like I already asserted, these off-diagonal zeros are the thing that says that there's no correlated noise, that the noise is independent. And so what do we have to do? We have to add off-diagonal elements to this matrix, and then we're done. That's the Gaussian process. Is just trying to add off-diagonal elements to this matrix. So how do we add off-diagonal elements to the matrix? So maybe you're in a situation where whoever collected the data could compute what those covariances were as introduced by their instrument. There might be time correlations or something like that, that you have some way of actually just writing down what this matrix should be. But most of the time, that's not true. Most of the time, we have to model the elements of that matrix. And you'd be probably at a loss if you tried to just like add a model parameter for every entry in this matrix. There's some, it has to be symmetric, so it can't be arbitrary, but that would be a lot of parameters, and it probably wouldn't work very well. So what's the approach that we take? What we do is we write down some function. So C nm, the nth element in that matrix. We actually often call this K at this point for reasons that I'll explain in a second. And we write some function that I'm going to call little k that depends on Tn and Tm, and it has some parameters alpha. That's the way that we normally write this. In fact, we might even go one step further and write this and add a Kronecker delta nm with our sigma n's along the diagonal. So this is a diagonal matrix here because this is 1 when n and m are equal and 0 otherwise. So this gives us a diagonal matrix that we had before, and then we're adding off diagonal elements through this function k, which I'm going to spend quite a bit of time talking about. Good. So this function is has lots of names. It's like a key part of this whole process. It's called the covariance function or the kernel function, and that's where the k comes from. And I'm going to probably use those terms completely interchangeably through the rest of this presentation. Under certain circumstances, that's actually quite common, would be to actually write k as just a function of Tn minus Tm. So just the differences in time. That's what's called a stationary covariance. And in that case, this is the autocorrelation function of the data. And so if you're looking at power spectra, for example, you would be working in a framework like this. It doesn't have to be. There are examples of covariance functions that don't depend just on the difference. But most of the time, we're working with stationary processes like this. Good. So this now gives us a way of evaluating all the elements of K, which we can then plug into this expression up here, which I'm going to rewrite using K now. And just to make things a little bit more clear, perhaps, I'm going to put a subscript alpha on the K so that we remember that it depends on the parameters alpha of the kernel function. And I'm going to put a theta on R to remember that that depends on theta. Alpha is, we'll give some examples in a second, but could be a vector. It's like a set of, it could be a set of integers. There are lots of different things that could specify it, but I'll give some examples. But great question. Yeah.
Yeah. So am I supposed to think of the sigmas as being how badly your model fits? I'm getting confused a little bit.
Great.
Yeah.
Yeah, good. So the sigmas here are the things that you calculate from the instrument. So like propagation of the photon noise through all of the data reduction process. These are handed to you by God.
This example,
Yeah.
Can you explain how the sigmas handed from you by God will be correlated?
So right, yeah, great. So these sigmas are not correlated, right? So here I'm saying that there's a diagonal component, which is the per measurement uncertainty, but then there's also some correlation introduced by the variability of the star and things like that. And so that's the part that's uncorrelated. Sorry, that is correlated, yeah. Now, of course, in real life, there probably are correlations caused by the instrument and the processing pipeline where I'm doing some like background subtraction that like correlates things. There are lots of things that you could imagine that would introduce other correlated noise that we often don't think about. But in sort of the framework that we're thinking about right now, the uncorrelated part is provided to us by the observatory or whatever. And we're trying to model the leftover correlated noise using this Gaussian process. Any other questions? Yeah.
So just a clarification about this, like about the noise. So here we're saying noise is not just instrumental noise, like all sources of noise, right? And so we're just dividing in correlated and non-correlated, wherever they come from. We don't care about that.
That's right. Yeah. Well, let's come back to that. Yeah, let's come back to that a little bit in a minute. But yeah, good point. Good. So I wanted to give some examples of the kinds of kernel functions that we might use, because that might sort of help clarify things a little bit. So one common, and I'm actually going to erase this as well. I think hopefully it's been up there long enough that we can sort of remember it vaguely. Okay, so one example would be, say, something like this, that I'm going to, okay, let's just do this. One example would be some a squared exp of minus Tn minus Tm over some L squared, L, just L. So an exponential kernel. So I've written DRW because this is the damped random walk, it's often called, or the OU process. The units of these things are interesting. So A has units of Y, whatever your Y-axis is. So in our transit fitting example, A has units of flux. And then L has units of X. So in our case, it would be units of time. So this is like the time scale of the process. This is the amplitude of the variability of the process. So there's some interpretability of these things. Another example is, maybe I shouldn't have it like, there we go. We have another example, would be something like, so this is often called the squared exponential kernel. And it looks very similar. We have an A that has units of flux. We have an L that has units of time, but we've squared everything here. Seems like it shouldn't make a huge difference, but it turns out that even though there's sort of similar interpretations of these two parameters, if you write down a Gaussian process with these, with this kernel or this one, you actually get very different behavior. And that has to do with the properties of how differentiable this function is. But in particular, this one has a lot of high frequency noise, and this one is extremely smooth. And so one way, sort of you're bringing in some opinions about what kinds of variability you can generate by the choice of kernel function that you use. And so one way of thinking about this is that what was I going to say? So the power spectrum for this is Gaussian, and the power spectrum for this is 1 over f squared. And so those have very different behavior at large frequencies, at high frequencies. And so you can often look at the power spectrum to get a sense for the kinds of behavior that you would expect in your time series. There are lots of other examples. So like one fun example would be, say, the cosine of Tn minus Tm. So the periodic kernel. And so here we have some some period of the variability, and the power spectrum for this is a delta function in Fourier domain at 2 pi over L, right? And so there are lots of examples. You can look at the paper that I referenced at the beginning for more examples. You can Google Gaussian process kernel functions to see all sorts of things. But what do we do with these? So once you've chosen one of these, you can plug it into that equation and evaluate the likelihood of your data. But normally, it's not enough to just use one of these functions. What we normally do is we actually construct some function, some kernel function that has sort of the properties that we want. So if you think there's some variability, some like damped variability in your time domain, you might take a cosine kernel times a squared exponential kernel, and then add a damped random walk kernel to capture some non-periodic variability or something like that. It turns out that any valid kernel function, if you take the sum and product of other valid kernel functions, gives you a new kernel function that is valid. And so you can end up constructing these very expressive models by combining these pieces together in interesting ways. And so that's a big part of using Gaussian processes. Yeah.
So by valid, you mean like you can construct a well-formed covariance matrix out of it, like it's positive definite and all these things.
Right. Yeah. So in practice, there are various constraints that are needed in order to generate something that doesn't give you nans or infinities, and you can write that down and validate it. It's like slightly non-trivial to do it, sort of in the general case, but yeah, exactly. It's sort of the general constraint is that it needs to generate positive definite matrices for K, positive semi-definite matrices for K. I think K's was next. Yeah.
Like when you say sum and product, like just linear order or like actually
So the question was any order of sums and products, or what about you mean like squaring or something like? Right. So remember, if you take the sum and product, you get a new kernel that's valid. So you can just keep doing that and stack them on top of each other. There are also other fun operations that you can do, like differentiation, integration, lots of fun, really fun things you can do. Vivian?
Yeah, I have, sorry, one more. What part of this is the Gaussian process? When we say the covariance,
Good, great question. So the question was, what about this is Gaussian processes? Good, great. So I don't entirely know. So like to some extent, like actually the first thing I wrote, the first likelihood function I wrote is an example of a Gaussian process. It's just like a pretty terrible one. And so to some extent, it's, in practice, the way people use Gaussian process, or like when they talk about Gaussian processes, they often mean that you have some covariance function that you can evaluate anywhere. So you can, even not just on your training data, you can also evaluate it, and that gives you this opportunity to interpolate and extrapolate in ways that are meaningful. But the Gaussian part really comes from the fact that this equation right here is just the log of the probability for a multivariate Gaussian. And we've filled in the entries to this matrix with some function. So people who are a little bit more rigorous might not totally agree, but I think it's the definition is pretty broad. I think Will was first. No. I can repeat.
I understand if I measure some quantity A and I measure some other quantity B, and then I think there's some, the covariance of the sum of the covariances. So I have this like mental model of how I would add kernels and what that like represents. What is the like measuring process or noise process that would give me a product of kernels? And how should I think about that?
Good. So Will was asking if we could come up with better intuition for what it means to take the product of Gaussian processes. The sum sort of has an intuitive feeling, sort of adding to random variables. What does taking the product, like, can we come up with a more intuitive description for that? And I don't think I can do that on the spot. Let's talk about it later. There's probably something very clever I could say right now. Savina.
Yeah, is there some rule of thumb to on how you choose the best kernel for your problem?
Great. Yeah. So let's come back to that. Yeah. I think not. No, let's say it right now. Okay, good. So briefly before I answer your question, the takeaway from this section that I want to make is that we've now written down this likelihood function, which I keep coming back to, and it's now a function of theta and alpha. But this separation of these two is sort of artificial. And so now anything we did with theta, we can now do with alpha too. And so we can put this into an optimizer and find the maximum likelihood values for theta and alpha simultaneously. We can run MCMC to marginalize over some quantities in here. This is, we can just use anywhere where we're doing chi-squared fitting. I said we could be fitting jitter. Anywhere we're doing chi-squared fitting, we can be using this. And so this leads into the question, which was, how do you choose your kernel? And I turn that back and say, how do you choose the model that you ever use when you're fitting data? What is the rule of thumb for that, right? And why is a Gaussian process special? And the answer is that it's probably not, right? So if you have like a physical description for what's going on, then writing down the kernel that describes that physical process as best you can is what you should use, right? Now the catch comes that sometimes we don't actually, like in my transiting planet example, a lot of the time I actually don't have a really good physical model for everything that's happening in that data set. Stars do all sorts of weird stuff, and the Kepler spacecraft does all sorts of weird stuff, and I don't necessarily have a good model for that. And so the approach that I generally take is I write down some flexible basis of kernel functions, and I do some sort of model comparison, or anything that you do for model validation in a normal data set, or with like a normal model, whatever that means, you can also do with this. So cross-validation, Bayesian evidence, all of those kinds of things are things that you can do with a Gaussian process. And that can give you a way of at least checking that you're choosing a better kernel than not having one at all, for example. Any other questions? Good. So basically, everyone should just use Gaussian processes all the time, right? You're fitting data, use a Gaussian process. Why not? The special case of A goes to 0 is what we had before. Remember that this second term right here is that normalization factor that's trading off against the goodness of fit. And so what that means is it's going to make the Gaussian process as non-specific as possible while still describing the data. So it has this sort of like protection from overfitting to some extent. We can go into more discussion about that over drinks. But yeah, just everyone should do it. It's great. Love Gaussian processes. So why not? Oh, no, wait. I have one more aside. Okay, yeah, I'm just going to say this really quickly. So I've been talking about T all the time here because my paper was about time series. I love time series. 1D is really nice. You can visualize everything. Not everyone here just works on 1D data all the time. So I wanted to say something about what happens if your input coordinates are no longer, we're replacing T by some X. All right, where that's some higher dimensional. I'm not talking about the output data being multi-dimensional. I'm happy to talk about, there are like methods for doing multi-output GPs, but I'm talking here about inputs being higher dimensional. So for example, coordinates on the sky or something like that. And then you have a 2D Gaussian process, or coordinates in a 3-dimensional box, something like that. Those are examples of multivariate GPs that you might want to do. So I'm not going to talk in too much detail about this, but basically, one useful way about thinking about multivariate GPs is to write your kernel function as some function of some other function, which I've called rho, which is a way of computing the distance between 2 points. So this is now a stationary Gaussian process if you can evaluate the distance between your points. And so, for example, you might take the Manhattan distance or the Euclidean distance, or if it's coordinates on the sky, you might take the Great Circle distance, or it can often be very useful to think about it that way. And then once you've computed the distance, you plug that into any of these equations right here. For where we have Tn minus Tm, you put in the distance. So it's all about writing the metric on your space. There are other kinds of GPs, but sort of a lot of the time it's easiest to think about it this way, that you write down a metric and then you evaluate the 1D kernel function. Of course, it's interesting because you can also, like this also enters in the 1D case, right? Like maybe your 1D inputs are, have periodic boundary conditions or something like that. You would want to write down a distance that could handle that, even in 1D. So it's, good. So everyone loves Gaussian processes. I was going to talk about predictions, but we're going to leave that off. That's okay. So why doesn't everyone use Gaussian processes all the time? In 5 minutes, in 3 minutes. No, it's not too bad. Okay, good. So there are a few reasons. I came up with a list. And the big one, that's my favorite one, that I'll talk about just a tiny bit, is the cost. And the problem is that, so here we're inverting or solving a linear system that is the size of your data, right? So K here is n data points by n data points. It's this big matrix. You have to invert it and compute its determinant. That is brutal, right? So that is very expensive to do, but it also scales poorly. So it scales, the computation cost scales with the cube of the size of your data set. And so that was sort of the big reason why this hasn't taken why didn't, not everyone uses it all the time. Okay. What are some other issues? How do you choose a kernel? Okay, we already talked about that. It's a question that we always get, how do you choose your kernel? I already said, you do all the usual things, you motivate your choices, and you do model checking. Great, we've solved that. No one's ever going to ask that question ever again. Good. Last one is non-Gaussianity. So let's say you have outliers in your data or something like that. What happens when you fit a Gauss, if your model is misspecified in such a way that you have non-Gaussian outliers, or maybe your physical process actually has non-Gaussianity in it? Your host. We can talk more about options there. I'm working. Things quickly become untractable when you don't have Gaussians. So the usual approach that I use, a lot of the time I'm working with data that has outliers in it. I would do some sort of sigma clipping or something like that. You can do the Gaussian process generalization of sigma clipping, which is not a really wonderful answer to that question, but it tends to be pretty practical. But we're not going to dwell on that too much. Okay, but I wanted to say just two more quick things about the cost. So so it turns out that we actually can do Gaussian processes on huge data sets, and we do. And so how do we do that? And what are some approaches that you, as a user of Gaussian processes, because you're all going to leave and use Gaussian processes, how would you use them? So one really great way to get better computational performance with your Gaussian processes is to be really lucky. So perhaps your data has some structure to it. For example, maybe your data points are uniformly spaced in your x coordinates. Turns out there are all sorts of fast things you can do to handle that case. Or maybe there's some other structure in your data such that it lives on a tensor product grid. Great, use that. That's going to make everything a lot faster, make your scaling better than n cubed. Great. Most of the time, we're not so lucky, especially in astronomy. So the second thing that's really good and that we do pretty well here is getting a better computer. So that can be good. If you have lots of computers, that's also good. And so that's another approach. Sometimes GPUs can really help. But again, there's some limit to like how much that can help you. And so the more realistic cases are that you can build. So perhaps your specific choice of kernel has some structure to it that you can exploit. So that's what I've mostly worked on. There's like a class of covariance functions that have some quasi-separable matrix structure. There's all sorts of fun math that we can do to get linear scaling computations of those kinds of GPs. And so we can scale that to millions of points, no problem. It's great, even on a laptop. But if you don't want to choose that specific kernel, sometimes you can use approximate methods that will, either subsample your data or approximate your data using one of these scalable methods or things like that. And I'm not going to talk about that specifically, but there's there are algorithms and libraries that exist for doing things like that. And so that can be sort of a good general point. So the last thing I wanted to say, yeah, great.
Good question.
Yeah, of course.
I'm surprised that Gaussian is such a problem because not really a sense, but
Yeah.
in kernels, it seems like those matrices are pretty banded. Aren't you usually?
Great. So the question is, what about banded? Like, is there structure in the data such that it's the matrix that you get would be banded? For example, if only nearby data points were correlated with each other, you might be able to use sparse linear algebra or some sort of banded linear algebra. And so that's true in some cases. In practice, in my experience, most cases that I work on have long enough covariances that you don't benefit very much from that. But it's very problem specific. So I should have mentioned that as well. Using sparse linear algebra systems can be really helpful if your problem satisfies that condition. Good, but I wanted to just finish by saying most recently, I've written about like 1,500 different Gaussian process libraries that in like Python and JavaScript and like whatever. And so if you want to use Gaussian processes, you should definitely use some of my code, even though there are lots of other things that exist. I do work here, so if you have problems, you can come complain to me. And of particular interest, I wanted to point you to something called TinyGP, which is the one I've mostly been working on. Recently, it was called that originally because I was trying to write a Gaussian process implementation with the fewest lines of code, or sort of the most lines of documentation divided by number of lines of code. It's sort of gone off the rails a little bit, so the name is a little bit less fitting, but I'm really proud of it, and it sort of implements some cost-saving things. It's got some other nice features, and so I would love it if people would use this, and I'd love to talk about that. But that's it. Thank you so much. do we have time for some questions, Megan, or do we? Okay, any questions?
So I just, as you mentioned earlier, the thetas and alphas could be switched either way. So I just didn't get a good sense of what is special about only modeling the covariance matrix and not just having an arbitrarily covariant complicated model that's some full
Great.
basis set that one could hope with always.
Yeah. So the question was, since the alphas and thetas can be swapped, why don't we just put all of the power into our f function? And why are we bothering with this Gaussian process? And we could use some, basis set or something like that of functions. And it turns out that actually a very common way of deriving Gaussian processes is by writing down a basis set of functions, taking the size of that basis to infinity under some reasonable prior choices that regularize the problem. And you end up with a Gaussian process under that case. So each of the kernel functions that I mentioned have some underlying basis set that they live in with some regularization prior on the elements of that set. And so it can sometimes, I actually don't find it very intuitive to think about the problems in that way, but some people do. And so this sort of gives you some way of not having to set the number of basis functions that you use or something like that. But there's a lot of similarity. Yeah. Any other questions? Yeah.
For number 3, would it be possible to use AGP to essentially model some weight parameters and then, for example, have equal distribution?
Great. Yeah. So the question was, in the case of non-Gaussianity, could we use the GP to model some latent parameters and then have some non-Gaussian observation model on top of that? And that's, I think, exactly the right way to think about it. The problem with that is that you lose a lot of, so then you have to do nonlinear inference on the true value of your function at the location of all of your data points. So the size of your parameter space now scales with the number of data points that you have in the data set. So practically, it can be hard to do that. There are lots of sort of clever tricks like using variational inference or things like that people have come up with for handling exactly that case. But I think that's a really interesting direction to think in. But it can sometimes be even more computationally intractable to actually execute that, even if it's a really good idea.